Hey guys, today I want to present a solution to a functional equation on points in the plane. At first, let's have a look on the problem statement. We have given a set S of a finite number of points such that there are at least 4 points in the set. And moreover, we have that no 3 points in the set are collinear and not all of them lie on a circle. Now we are asked to find all functions from the set S into the real numbers such that if we take a circle that contains at least 3 points in S, the sum over all these points of f of p should be equal to 0. When starting with this problem, I want to note at first that the condition that no 3 points from the set S are collinear implies that whenever we choose 3 points out of the set S, we know that there exists exactly one circle going through these points. Taking a look at this condition here, we see that if our function has at every point the value 0, then this must clearly hold for every circle at C, and therefore we already figured out our first solution, namely that f of p is equal to 0 for every point p in S. On the other hand, if we find a point p in the set S such that f of p is not equal to 0, so for instance f of p is greater than 0, it feels like we can just choose 3 points such that the values of the function of these 3 points are maximal, and then take the circle around these 3 points and get a contradiction to this condition here. Clearly, that does not solve the problem, because for example, then there can be a lot more points on the circle, and then this condition here is not more so strong. But nonetheless, it's a good idea to consider such cases, and therefore at first, for the sake of contradiction, we want to assume that we find a point p such that f of p is not equal to 0. As I said, it feels like a good idea, in order to get a contradiction, to consider some p such that these values of f of p are really large or really small, and therefore we want to choose p1 and p2 in such a way that the absolute value of f of p1 plus f of p2, which I want to define to be m, should be maximal. We want to confirm that m is indeed not equal to 0, and therefore assume otherwise that m is equal to 0. This would mean that for any other point q in S, we would have that f of q is equal to minus f of p, but this is clearly not possible, because then we can just choose some arbitrary circle going through 3 points not equal to p, and then this is a contradiction to this condition here, and therefore we have that m is not equal to 0. For convenience, you want that f of p1 plus f of p2 is indeed greater than 0, and we can assume this without loss of generality, because otherwise we can just have a look on the function minus f. So without loss of generality, we have that f of p1 plus f of p2 is equal to n. Together with the condition that for any circle through 3 points in S, we have that the sum over all points on this circle is equal to 0. We get that if we take some circle going through p1 and p2, the sum of all other function values of the other points on the circle must be equal to minus m. I have drawn in a picture to visualize this. Here we have the points p1 and p2, and now we have 3 circles going through p1, p2 and at least one more point. And now we know that the functional values of these 3 points here sum up to minus m. Then for this point the functional value is minus m, and for these 2 points the functional value sums up also to minus m. And to have a better notation, I want to give the sets remains. So I call this set here S1, this set here S2, and this set here S3. In general, this is a partition of all the points in the set S not containing P1 and P2 in such a way that 2 points are in the same set if P1, P2 and these 2 points are concyclic. Then we get that the sum of f of p for all points p in one of our sets Si must be equal to minus m, which is less than 0. The fact that not all of the points lie on one circle tells us that we have here at least 2 different sets, and therefore if we name the sets S1, S2, and so on up to Sk, we know that k is greater than or equal to 2. This implies that the sum of f of p over all points p in S is equal to f of p1 plus f of p2 plus the sum over all indices going from I equals to 1 up to k of the sum of all points p in Si of f of p. And now we use this equation here, which tells us that this is equal to, at first here we have m plus k times minus m, and now since k is greater than or equal to 2, this is clearly less than 0. At this point, if we can find 2 points q1 and q2 in our set S, such that the sum here f of q1 plus f of q2 is less than 0, then with the same argument we could conclude that the sum of all points of the function values must be greater than 0. So if we find such 2 points, we are done. To find such 2 points, we remember that the sum of f of p over all points p in the set Si is negative, and therefore we find some qi in Si such that f of qi is less than 0. Because k is greater than or equal to 2, we know that indeed f of q1 plus f of q2 is less than 0, and therefore with the same argument as this here, we can get that this sum here is greater than 0, and this is clearly a contradiction, and therefore f of p equals 0 for all p in S is our only solution, and we are done.